We are talking today about what we do with streamflow data once we have it. So earlier this week, we talked about what it takes to get good discharge data, how the USGS ensures that they have good quality data from stations like this one, shown in the picture up in Alaska. And now that you have the data, you know how to download it from the web. What the heck do you do with it? So I'm going to call this part one of a two-part video sequence on analyses that hydrologists can do with streamflow data. This isn't going to be an exhaustive list of analyses or things that we can do. And today's video is going to start with some really, really basic things. All right, so the first thing you could do with streamflow data once you've downloaded it from the USGS or you've created it from your own fieldwork is graph it up. And of course, we call a graph of discharge or streamflow over time a hydrograph, right? So this is an example of one pulled from the Roaring River in North Carolina. And there's a couple things I want to point out, features of this hydrograph. One thing is that if you are getting data from the USGS or other US government data sources, you're going to see the units in cubic feet per second. Of course, the rest of the world works in metric, and assignments for my class I ask you to do in metric, so that would be cubic meters per second would be a good unit to use. The other thing you should notice about this graph is that it has a log axis, right? So between 10 and 100, the tick marks or lines are going up in units of 10. Then between 100 and 1000, they go up in units of 100. So this is 100, 200, 300, 400, and so on. And then between 1000 and 10,000, they go up in units of 1,000 cubic feet per second. And notice that the lines aren't equally spaced apart. That allows you to see variations in the high flow portion of the hydrograph and also variations in the low flow portion of the hydrograph. If we didn't have this log y-axis, then all of the low flow would be really squished together, and what you'd really see is that this is a really big flow over here, this is kind of a big flow, and then everything else would just look very small. So we're essentially distorting the data in order to see the variability in streamflow. All right, the next thing you could do is create a different form of hydrograph, and I'll show you this in a second. We call it a unit hydrograph. So the key difference here is that you're going to take your discharge or streamflow number and you're going to divide it by your watershed area. So this is really useful when we want to compare multiple watersheds to each other. If you have a watershed that has an area of 10 square kilometers and another watershed that has an area of 100 square kilometers, the data from the bigger watershed, assuming the same climate, is going to have higher streamflow. But what do they actually look like if you divide by watershed area? That's why we make a unit hydrograph. And I'll show you how this transforms the way your data looks and the information you get from it in a minute. Just so you are thinking about units, if we are in the metric system, you might have units of cubic meters per second per square kilometer. The advantage of that unit and notation is it lets you easily see that discharge is divided by area. Of course, it's not a simplified fraction, so you could simplify to things like millimeters per second or millimeters per hour, making sure to pay attention to all of your unit conversions. And the nice thing about this is it's simplifying things down so that it's a linear rate. You could think of this as very comparable to the way we think about rainfall. Okay, so this is example hydrograph. This is showing 3 forms of green infrastructure at a single site for a single storm. So we actually have a hydrograph, right? Rainfall coming down from the sky here in blue. And then we have flow coming off a green roof and 2 different bioretention cells, all receiving the same rainfall. And this is in units of cubic meters per second. So yes, the flows are pretty small. These have pretty small drainage areas, but what you see there is that the green roof appears to have very small amount of flow coming off of it relative to the flow coming out of the base of the bioretention cells. But how will our perception of this hydrology change when we change to a unit hydrograph? All right, so here's the same data, same storm, same rainfall, same sites, but now we have divided each of these catchments by their catchment area. So the green roof's just the space of the roof, whereas the bioretention cells are the bioretention cells plus the parking lots that drain into them. And now we get a very different picture, because rather than thinking that the green roof is a small player, what we see is that the green roof per unit area is producing a lot more runoff than the bioretention cells. That the bioretention cells are pretty similar to each other, but man, the green roof responds faster and it produces a lot higher flow per unit area than the bioretention cells. Now, if we're interested then in controlling stormwater, we might say that green roof doesn't appear to do as good a job at controlling stormwater as the bioretention cells. And that's the power of the unit hydrograph. It lets us make these comparisons against things that have different watershed areas. All right, let's have a bit of a side about the graphics of hydrographs. It's really easy to take data, stick it into Excel, use the defaults, and make some really, really terrible graphs. So there's a lot of things wrong with this graph. We could probably go on for it about several minutes, not labeling axes. Notice that it's a linear y-axis here, and this is what I mean. This is actually that same Roaring River hydrograph that I showed you from the USGS, so we can see that when we don't use a log y-axis, we lose a lot of our ability to perceive differences in the low flow and moderate flow portion of the hydrograph. Another thing that I really dislike about this hydrograph is that we've let Excel choose our minimum and maximum values for the x-axis, and that makes it look like the stream just stops, and then it suddenly starts in October 2007, and then what? The stream ends in September 2008? Obviously, that's not real. So what we can do is we can adjust this so that we see that we are only seeing an excerpt from the total streamflow record by adjusting the minimum and maximum values on the x-axis within Excel. So here is the same data again. Now it's been graphed up as a unit hydrograph. I think that this is a much more pleasing representation of things. We see a little bit nicer color choice, not such obtrusive grid lines. We have nice tick marks representing our variation in our log y-axis, and this is what I mean about adjusting our start and end points on our hydrograph so that we don't have this sort of misrepresentation of flow starting and stopping just at the beginning and the end of the data set we've chosen to analyze. And again, look at that difference between the log y-axis and the non-log y-axis in the way we see that variation in the low flow part of the streamflow record. All right, I've actually already showed you the next thing you could do with streamflow data. If you have streamflow data and precipitation data from a rain gauge, you can take a hydrograph of a storm and have a hydrograph or a rainfall graph coming down from the sky or sticking up from the bottom. And this sort of representation is really useful to see how peak flow timing and peak flow amounts correspond to our rainfall time series. So here we can see in this example storm that it starts raining, the flow starts to rise. You can see some rises and falls in the flow associated with changing intensities of the precipitation. Then you get this intense precipitation, and then the flow declines thereafter. And what's kind of interesting about this particular example that isn't my data is that we get a peak in the flow before we get our peak rainfall intensity. So not quite sure what's going on in that watershed, but that's the sort of information. Now we can really see this difference in timing and magnitude between precipitation and stream flow when we graph the two time series together. And anything we can make a graph for, we can also calculate statistics or pull the numbers out, right? So we could actually start to make a table or statistics about peak flow versus peak rainfall, or timing of peak flow versus timing of peak rainfall. So lots and lots of things that we can do here, looking at the relationship between rainfall and runoff response. Let's go to something that is a little bit more abstract. All of the things that we've looked at so far have just used our time series of flow data as a time series, but sometimes we want to get an idea of something that isn't just the flow over time. So we're not so focused on the rises and falls in response to particular precipitation events, but we're trying to really understand the shape of the stream flow or the distribution of the stream flow over longer periods of time. And a flow duration curve, or FDC, flow duration curve, is a really useful way of looking at that, because what it does is it shows the probability that a particular flow will be equaled or exceeded based on the stream gauge record. So this is a really nice, cool example of a flow duration curve for the Root River in southern Minnesota. This is actually the river I grew up canoeing on with my family. And one of the things that we can really clearly see from this flow duration curve, which they've broken out by decades here, right, is that flow is increasing over time. So the way this works is that you have low flows at this end of things, so the lowest flows are exceeded nearly 100% of the time, and the highest flows over here are only very, very rarely exceeded, right? Only a small percentage of the time is a stream having really high or flood flows, and most of the time it's having more moderate flows, so that by the time we get to the lowest flows, they're exceeded 100% of the time. And so what this does is it lets us see that over these decades on the Root River, not only are we getting bigger floods, or maybe we're getting bigger floods, but we're really seeing this increase in the low flow and the moderate flows, the sort of middle of the range flows on the Root River, and that's particularly picking up in the 1990s and 2000s relative to the earlier decades in this signal. So there's some interdecadal climate variability here, but then something has really changed in the 1990s and 2000s in terms of climate or land use in this watershed that's caused there to just be more flow in the river. And again, I've left the same little notation over here. Anything that we can make a graph of, and I'll show you how to make this graph, we can also calculate statistics for. And so you see some examples here where they're saying at the really low flow end of the spectrum, there is a 80% increase in these low flows, flows that are exceeded 90% of the time, between the early part of the 20th century and the present day. And so we can calculate a percent change for a particular exceedance probability, or we can just simply look at the discharge for a particular exceedance probability. So let's look at another example. Okay, so here is a pair of flow duration curves. So now this is two different watersheds. We've got sort of a very English unit discharge over here, cubic feet per second per square mile. That lets us compare these two watersheds that have different drainage areas to them. These are watersheds that I studied for my PhD, and they're really interesting because they're adjacent to each other, but their geology is slightly different. So the Clear Lake watershed has lots of young lava flows and lots of groundwater flow in it. And the Smith River watershed is older and steeper and has a lot of shallow subsurface storm flow in it. And so what we can see then is that there's some similarities in these flow duration curves and some differences. So some interesting animation there. So one of the big things that should be jumping out at you is this low flow end of the spectrum. So Again, the low flow, so low on the y-axis, has a high probability of being exceeded. And so we could pull out any particular percentile that we are interested in and say, this is the flow exceeded 90% of the time. We call that the Q90. And we can sort of drop a vertical line on our graph, and we can read the Q90 out for these two streams. So in the Smith River subsurface storm flow dominated stream, the Q90 is about 0.12 or 0.22 cubic feet per second per square mile, whereas in the Clear Lake watershed, it's about 2 cubic feet per second per square mile. So there's an order of magnitude difference in the low flows between these two streams. So that's just an example at the low flow end of things. We could define a Q80 or a Q70 or a Q10. We often use the Q10, so flow exceeded 10% of the time, to talk about the high flow end of the flow duration curve. So if we sort of visually go up here, we see that the high flows are lower in our groundwater dominated watersheds, so they might be on the order of 8 cubic feet per second per square mile, whereas 10% of the time in our subsurface storm flow dominated watershed, they might be more like 13 cubic feet per second per square mile. And when we get to the really high end, the infrequent flows, high flows, we see these big differences because of these different stream flow generation mechanisms. And again, we can read things the other way as well. So we might say, it's really relevant when flow exceeds, say, 10 cubic feet per second per square mile. So I want to know how often that occurs. I've just pulled that number out of thin air. In a unit discharge context, it might not make a lot of sense, but you might imagine something like wanting to know how often flow exceeded the design capacity for a culvert. And so a flow duration curve would let you know that. So in this case, if we look at just how often flow exceeds 10 cubic feet per second per square mile, we see that in the Smith River watershed, the Green watershed, it's exceeded about 19% of the time, whereas that same flow is exceeded only, say, 7% of the time in the groundwater dominated Clear Lake watershed. So that's the other way we can read these graphs once we have them. A few other things to point out. I've got some interesting animations here. The median flow makes sense. So median is the 50th percentile of the distribution. So the median flow is the flow exceeded 50% of the time. And we can see actually just in our two example watersheds, they're very similar to each other. These, as I said, these watersheds are adjacent. They have the same climate, the same elevation range, much of the same vegetation, so it makes sense that they'd be very similar. But if I took the data that underlie this graph and I calculated the average flow over time, I would not get this median, and I would not necessarily get a number that was identical to each other. So because we're looking at things in a log-log space, these high flows are so much bigger than our low flows that the average is pulled toward the high flows. And so oftentimes your average, or just to add up all the numbers and divide by the number of numbers, that tends to have a probability something like 25% of the time. And so if we took the average of these two watersheds, rather than being quite similar, we might see a little bit bigger difference because the Smith River just generates so much bigger floods than the groundwater dominated Clear Lake watershed. All right, so how would you create your own flow duration curve? You're going to download data for a period of record from a stream gauge, maybe on the USGS website. You're going to bring it into the spreadsheet program of your choice, and you're going to sort the data from the highest flows to the lowest flows, so that your biggest flows are at the top of the spreadsheet. And then you're going to apply a rank to each of the data. So your biggest flow is rank 1, your second biggest flow is rank 2, your third biggest flow is rank 3, and so on all the way down through your data set. So if you're working with daily data and you have 1 year of data that you're looking at, you're going to have ranks 1 through 365. Now there are some nuance if you've got ties in your data set. Let's say flow is 20 cubic feet per second on 3 days in your data set. There are some ways you can deal with that. For my class, don't worry about the ties. It's going to make very little difference in your results. Okay, so you've ranked your data from 1 down to your smallest for 1 year, 365. You're now going to apply a probability formula. So what you're going to do is you're going to use your rankings, say M is your rank, and you're going to divide it by the number of data points plus 1. So again, if you're using 1 year of data, and there's 365 days in the year, you're going to divide each data point's rank by 366. We add this 1 on the bottom because what we're trying to say is, you know what, there's some possibility the flow could get lower than what we have seen in this historical data set. We're making an unbiased estimator of the distribution by adding this plus 1. So for your highest flow with rank 1, the probability is going to be 1 over the number of points in your data set plus 1. So if it's 1 year, it's going to be 1 over 366. The probability of your second highest point is going to be 2 over 366. All the way down to your lowest, your smallest flow, it'll be 365 over 366 for 1 year, non-leap year of data. Right? And that P is your exceedance probability. So if we go back to the graphs, the exceedance probability is what's going on your x-axis, and the flow associated with that exceedance probability is what's going on your y-axis. Right. And again, in simple terms, the exceedance probability is how likely is it the flow will get to be equal to or bigger than a given discharge. And just as a heads up, we're going to be revisiting this idea of exceedance probability next week when we talk about flood frequency analysis. So now you've got a column with exceedance probability and you have a column with flow, and you're just going to make your graph in Excel with a log y-axis and a linear x-axis. And speaking of graphical pet peeves of mine, notice that this axis goes from 0 to 1. Excel, it could be percentile, 0 to 100%, that's fine, same idea. But don't let Excel give you a 120% probability of exceedance because, of course, that's physically impossible for the way we're doing this math. So flow duration curves are a great way of starting to think about the range of variability. If you just want to kind of say, overall, how much flow do we have in a watershed relative to the precipitation in the watershed, we can calculate a runoff ratio. So the runoff ratio is the annual stream flow. So add up all the stream flow over the course of the year, keeping track of your units, and divide it by your annual precipitation. All right. Obviously, it's going to be best to use a unit discharge here so that and pay attention to your units and annual precipitation. So your runoff ratio can vary from 0 to 1. A runoff ratio of 0 would mean that there was no stream flow. No matter how much precipitation there was no stream flow. And a runoff ratio of 1 would mean that all of the rainfall that fell in your watershed was converted to stream flow. Okay, neither of these are super realistic. Even for the most urban paved catchment, you don't quite get a runoff ratio of 1. And the runoff ratio you do get depends on the climate and the vegetation and the land use in your watershed. And so this really nice analysis from a few years ago showing the distribution of runoff ratios in the United States. And you can really clearly see the climate signals in here. So these Great Plains watersheds have low runoff ratios, and the wettest parts of the United States, like the western side of the Cascades in the Pacific Northwest, have quite high runoff ratios. So maybe 2/3 of the precipitation is converted to streamflow. Another way of thinking about this runoff ratio is that it's telling you about the water budget, because where is the water going? If it's not going into streamflow, it's going to evapotranspiration. So another way of looking at this runoff ratio information is that it's giving us information about the evapotranspiration. It's saying that most of the precipitation that falls on the Great Plains gets used by plants and very little is left for streams. Whereas in the Pacific Northwest, there's so much precipitation that plants can have plenty of water and streams can too. All right. So we can do these runoff ratios on an annual timescale. You could also think about doing it on a seasonal timescale as well. And so you might see very different runoff ratios when the leaves are on and the plants are evapotranspiring in the summer than you do in winter when the plants are dormant and ET rates are lower. And that is actually one of the explanations for what goes on in the southeast, where we have pretty constant precipitation all year round, but our runoff ratios are much higher in the winter than in the summer because ET just takes so much water out of the streams in the summer. All right, so that is the sort of quick run through of the most basic analyses that you can do with streamflow data: create hydrographs, create flow duration curves, calculate runoff ratios. These are incredibly powerful tools for getting a sense of what your streamflow regime is in your watershed, getting a sense of the overall hydrology of your watershed, and you can do an awful lot just with hydrographs and flow duration curves. And if you're in my class this semester, that's what you need to know to complete problem set 10. But there are other things that you can do, more sophisticated analyses with recession analysis and hydrograph separation using data for numerical modeling, and we will cover those in part 2 of this lecture next week.